All right, let's get going, man. Seafloor spreading and transform faults. Chapter 4, and introducing the new subdiscipline of marine geology. So there were four groups of people that led the advance to our understanding of seafloor spreading. They were Tharp and Heezen, who worked out ridge bathymetry. Bathymetry, remember, is topography underwater. And they noticed we had enough information about especially the mid-Atlantic ridge, to talk about its bathymetry, what it looked like. That was in the late 1950s. So this is all being done in the background of continental drift, trying to understand whether it happened and if so, how. Then Hess and Dietz developed the idea of seafloor spreading in the early 1960s. Then Vine-Matthews-Morley developed the idea of seafloor, a magnetic fabric, and what caused it. But this required that people on land worked out the record of magnetic reversals. And that was Cox and Dalrymple. And then Wilson added the understanding of transform faults in 1965. So the things we'll talk about today were basically worked out in the mid 1960s. And, these were all marine geologists, sort of working at oceanographic institutions. Well, Wilson wasn't. But Tharp and Heezen were, Hess and Dietz. Hess was at Princeton, Dietz was at Scripps. And then Vine-Matthews-Morley, they were geophysicists. But so this new realm of the marine geology really took off from these kinds of studies. All right, so this is the mid-ocean ridge system, and you can see it's named after what's in the Atlantic, because in the Atlantic, the spreading ridge, the divergent plate boundary, is right in the middle of the ocean. That's not true in the Pacific. It's mostly true in the Indian. This is our present understanding, and what you'll see is the solid thick lines are the spreading segments. The narrow straight lines are transform faults, and the lines with barbs are convergent plate margins, marking where the plate is going down. And this is our modern understanding, not what they knew back 60 years ago. But altogether, there's about 40,000 kilometers of spreading ridges. And as I said, it's not always in the middle of the ocean. Nearly all of them are deeply submerged underwater. The only places they poke up above sea level is in Iceland in the North Atlantic, and then in East Africa, in Eritrea and Ethiopia. How do we figure this out? Okay, geologists were coming to the idea that the continents did move with respect to each other, but still the question was how? How is this possible? So by the late 1950s, many geoscientists were perplexed by the understanding that there was strong evidence for continental drift, but the mechanism was baffling. The answer had to lie in the ocean basins, but how do geologists study rocks of the ocean, of the seafloor? Geologists, are land creatures. They're very happy on land. They don't mind taking a dip in the ocean, but they're not going to go down to the mean depth of the seafloor of 3,800 meters, much less the deepest point, the Challenger Deep, 11,000 meters, which we studied this last end of November and December. Then you could take scuba, but that'll only get you down 330 meters. That's the deepest scuba dive on record. So how do we study seafloor geology? And basically what was required was we had to invent the field of marine geology. How did we do that? All right, well, we started needing to do things on the seafloor. So this started with industry, and as we'll see, was carried on by the military. So whalers knew something about the tremendous depth of the oceans because, after they'd harpooned the whale, all of this line would pay out and they'd go, geez, we're out of line, and they still haven't reached the bottom. So there was some idea of the tremendous deep depth of the ocean, but not any detail. But when it came time to lay the first transatlantic telegraph cable, all of a sudden we started to understand something about the seafloor. So the first electronic communication device was the telegraph, which was invented in 1839. The transatlantic telegraph cable from Newfoundland to Ireland was first laid in 1857, 1858. It lasted 3 weeks and broke, and a new cable was laid in 1865, 66. And that linked England with the United States, and it took off from there. That was definitely a growth industry. So in 1855, a bathymetric chart was published by the U.S. Navy Lieutenant Matthew-Morley. He revealed the first existence of an underwater mountain in the central Atlantic. Now, the way they did this is they would stop the ship, and they would attach a lead weight with a bit of wax to it and lower it and try and feel when it hit bottom. And they would confirm that it hit bottom because the wax usually picked up some stuff on the bottom, which it wouldn't if it didn't reach the bottom. So this is very laborious. Maybe you get to do one of these a day or two of these a day. But this feature, which we now recognize as the Mid-Atlantic Ridge, was picked up. And there's Iceland, the ridge comes down like this. Now, what really developed marine geology and was the development of sonar. So sonar is sound, navigation and ranging. Sonar, you'll see that word sort of go on with radar, LiDAR. Those are different energy sources used to illuminate things, but sonar was the first. And sonar was developed because of World War I, when the German U-boats, caused such devastation on shipping between England and the United States. More than 5,000 ships were sunk by German U-boats in World War I, with a loss of 15,000 lives. And in World War II, they sunk fewer ships but killed more people. And then Soviet submarines were a threat during the Cold War. And sonar was one of the key technologies invented to deal with this threat, which actually solved the problem. So sonar was designed for finding submarines, but it also would get, basically you send out a sound and listen for the echoes, right? Something big like a submarine is going to, some of the sound is going to bounce off it. So you can, start to figure out where the submarine is with this kind of technology. Now, like many things that we'll see that were developed in the military, this technology was soon adapted for science. So this is one of the earliest diagrams of echo sounding. This is called echo sounding. They're not looking for submarines, but they're using the same sound source. So they send out a pulse of sound from one side of the ship, or looks like, and then listen for it on the other, right? The technology right now is, the receiver and the transmitter and the receiver are in the same place, but back then they were just working it out. So this was in 1928, the Meteor expedition, and it's very, very simple. You send out a sound and you listen for the echo, and the depth to the seafloor is equal to the time times the velocity divided by 2, right? So, it takes time for that to bounce, and that's going to be a function of velocity, and you have to divide it by 2 since it's 2 ways. So, sonar pulse sent out, and an echo takes 5 seconds to return. How deep is the bottom? Well, you don't have enough information, but that's kind of a very simple statement of the problem. All right, so here's a velocity, sound velocity in water. So this is meters per second. So that's about 1.5 kilometers per second. compare that with the seismic velocity in the crust, which is on the order of 6 kilometers per second. So there is some subtle structure in the sound velocity, right? There's this minimum here at about, what is that, 750 meters depth, and then it gets higher and higher down. But if you assume we've assumed this is 1.5. Okay, it could be 1.5. Doesn't matter. But anyway, for this calculation, we assume the velocity is 1.55 kilometers per second. And so we can do the calculation now. The velocity in sound, 1.55 kilometers a second. So the depth is 5 seconds times 1.55 divided by 2. So 3.875 kilometers. That's how deep it is at that point. Okay. Any questions about that? Very simple calculation. All right. So this is a state-of-the-art bathymetric map in 1948. So Harry Hess was in the Navy, and there were a lot of battles in this part of the world. There's Japan. So Saipan was one of the biggest battles, was right there. Iwo Jima was another bad battle there. Okinawa, another battle over here. So U.S. Navy ships were going back and forth. They always had their sonar on because there were Japanese submarines operating in the area. And Harry Hess was a geologist who knew, with that information, I could do some interesting work. And he did. This is a 1948 map of we'll see this again and again. This is the Philippine Sea plate, right? He didn't know anything about plate tectonics. Nobody did. But there's the trenches in black, right? This is the trench where we were working last November and December. And these are volcanoes. So this is what we thought about this area looked like. And when we saw this map, this was quite remarkable because, this is a bathymetry map of a huge area. All right, and here we're comparing the 1948 version with what we can do today. And obviously the level of detail in the modern map is spectacular. You can see all sorts of structures. You'd have to zoom in, but you can see these ridges. He had no problem picking out these ridges where the Mariana Arc is, and this submarine ridge, and then another ridge over here, and these structures. Really quite remarkable. All right, now a fellow by the name of Arthur Holmes in Britain suggested something like this, but he kind of buried it in a publication, The Transactions of the Geologic Society of Glasgow, which is not one of your leading scientific publications. And what you can see is considering this is 100 years ago almost, this looks an awful lot like what we recognize as seafloor spreading. And you can see what he wanted to do. Here's a continental block. We can imagine that's Pangea. And then here is it broken apart. And he's recognizing the new ocean formed between it. And this island swell, or what we might call the mid-Atlantic ridge, is identified in this as sort of a remnant of the continent. He was wrong in that level. We're always wrong. It's just a question, are we more right than the previous interpretations were? And in this case, it clearly was, but it didn't catch on because it was kind of buried in this low visibility journal. Unfortunate, because that's basically the mechanism that Wegener and people that were in favor of continental drift needed. Now, a very important clue came from earthquakes. So this is a map of earthquakes, little black dots. And scientists had known for quite some time that seismicity marks where the Earth's lithosphere is breaking. And we're going to hear more about this in future lectures. but you can see they're not randomly distributed. They're concentrated in zones, right? So one way to interpret that, the reason there's not so many down here is there's just not so many seismic stations. You know, there's lots of seismic stations up here, so they're much more sensitive to these earthquakes, much less sensitive to these. And, you know, then we have these zones in here. So, you know, this was 1954. French seismologists published this map to show the concentration of earthquakes along the zones. And we now know that, especially the ones in the oceans, represent the plate boundaries. These regions on the continents are not as well defined, and we're going to discuss that. You know, but this belt here is basically a mountain belt, lots of earthquakes. You know, the Andes also have a lot of earthquakes. So let's talk about Tharp and Heezen. Marie Tharp and Bruce Heezen now are looking at their map of the Mid-Atlantic Ridge. And they published their first physiographic map of the North Atlantic in 1957. And then they started collaborating with an Austrian landscape artist and published a map of the entire ocean floor in 1977. And when you go downstairs outside of my lab, you'll see two maps. One of them, which is their original map, and the other one is a more modern version of it next to each other. And if you want to read about the experiences of this woman, who was very unusual, right? This was not the science was not very welcoming to women in the 1950s and into the 1960s. But if you want to read her biography, there's a book called Soundings by Hallie Felt, 2012, if you want to read about her experiences. All right, so at first, she noticed that the Mid-Atlantic Ridge had a morphology right up here on the top, going from Brazil to Africa, that sort of there's the high, but in the high there was a low, this region here. And she noticed that was very similar to Lake Tanganyika and the East African Rift Valley. And so she suggested to Heezen that it was a rift, and he resisted. He didn't like that idea, but eventually she convinced him. And we knew from East Africa and other rifts that these are regions where the crust and the lithosphere are pulling apart. So that became sort of accepted, that somehow things are extensional here. Now, building on that, Hess and Dietz developed the idea of seafloor spreading in the early 1960s. And this is an interest. All of these stories have interesting personality things. Like with Tharp and Heezen, it was women trying to be taken seriously by men. Hess and Dietz, they're both men, but one of them is treated like he didn't do anything, and the other one gets all the glory. And we'll talk more about Vine-Matthews-Morley, the lessons they tell us in a second. But Hess and Dietz and seafloor spreading, that's an interesting story. So Harry Hess, remember we saw him as a younger man back here, right? That's the same guy. And so he was definitely a geologist at Princeton. And in 1960, he made his single most important contribution when he advanced the theory, now generally accepted, that Earth's crust moves laterally away from long, volcanically active oceanic ridges. And this is what we now call seafloor spreading. So he was a professor at Princeton, so his work was taken seriously by other scientists, right? Now, Bob Dietz was, he deserves to share credit with Hess, and he often doesn't. And he was a remarkable geologist. He was the first to recognize the fact that the moon's surface was caused by meteorite impacts. He was the one that started to understand the significance of continental shelves and slopes. He understood things called shatterchrones as indicators of meteorite impact in the geologic record. Astrobleams, those are impact sites. But what we're going to talk about here is his paper in 1961 on continent and ocean basin evolution by spreading of the seafloor. So that actually was the first paper to develop the idea, and Hess came along later and in 1962 and never used the word seafloor spreading. Dietz uses the term spreading seafloor, not seafloor spreading. Hess never uses either. And nevertheless, Hess gets the credit for the idea, even though A, he never uses the term, and B, his study came a year later than Dietz's. But you know, the world is funny that way. So this is his interpretation of what's happening beneath mid-ocean ridges. He thought that what was happening was the mantle was coming up along upwelling convection currents and then moving laterally, and the top of the mantle was interacting with seawater and turning into serpentinite. And we'll talk more about serpentinite later, but basically it's an alteration product of olivine-rich lithologies like dunite or peridotite. So the seafloor spreading hypothesis was the paradigm shift that led to plate tectonics. And the idea of a paradigm shift, we hear it a lot, but it has got an interesting history. And it comes from a paper, a book called The Structure of Scientific Revolutions by Thomas Kuhn, who explains that science evolves via phases of paradigm, confusion, revolution, and then a new paradigm is established. And a paradigm is a theory that best explains the facts. When new facts come to light that do not fit the prevailing paradigm, scientists become confused and we argue a lot. Young scientists tend to embrace the new paradigm and old scientists tend to resist it. And this is something that was recognized a while ago. That's Max Planck has a very famous quote, 1948, "Science advances one funeral at a time," which is, you'd say, well, that's very dark humor. But on the other hand, it's true because, you know, old professors tend to have their ideas, and the ideas they embraced when they were young have a special affection for them. And so they tend to, many of us tend to make life difficult for young people who have different ideas. And that's why Max Planck said this. Eventually, a new paradigm replaces the old one, and another period of what Kuhn calls normal science, which is working within the framework of an accepted model, begins. In the case of earth science, a massive amount of new data about the seafloor, much of it the direct result of defense technology, was collected after World War II, including bathymetry, magnetism, and seismology. And this new information led to confusion in the geoscientific community during the 50s and 60s, but was eventually resolved by the Dietz-Hess ideas about seafloor spreading. So this new paradigm led to the understanding that Earth's surface was a patchwork of lithospheric fragments called plates. The new paradigm of plate tectonics explained the puzzling post-war facts and opened up fresh lines of inquiry. In Kuhn's terminology, geoscientists today are mopping up, elaborating on the plate tectonic model, filling in gaps, but without radically altering the new paradigm outlined by Dietz and Hess in the early 1960s. All right, so what we now understand is that spreading occurs along the summits of broad, gentle spreading ridges. These are also called divergent plate boundaries. They're called mid-ocean ridges, although the only ridge that's really in the middle of the ocean is the one in the Atlantic. and to a certain extent, the one in the Indian, whereas it's not in the East Pacific. So there it's called the East Pacific Rise. And you'll notice some differences. One of them is how steep and rugged the Mid-Atlantic Ridge area is compared to the East Pacific Rise, how smooth that is, relatively speaking, and how there's no axial rift. Whereas in the Mid-Atlantic Ridge, there's definitely one. And this is an old paper, but it nevertheless, those profiles are still useful. So the dawn of the 21st century witnessed a technological trifecta in mapping the seafloor. So the result of this is that modern marine geoscientists now have the tools that let us do field work on field geology on the seafloor. We are in the throes of a modern revolution in seafloor geosciences, and it is the new generation of marine geoscientists that stand to benefit the most. All right, so what is a trifecta? So in horse racing, picking the horse that comes in first, second, and third in a race is a trifecta. And as you can imagine, it pays off very well. So here is the marine geologic trifecta. Now, with GPS, we know exactly where we are in the oceans. Previously, it was very difficult to locate yourself at sea. You'd have to use astrolabes and take sun sightings, and you were always off by a few miles. Now we know to where we are, to centimeters. So number one, you can navigate to exactly where you want to be. Number two, we now do something called swath mapping, and I'll explain more about what this is. This allows us to map broad swaths of the seafloor from the ship in real time. And finally, we have technology that allows us to go to the bottom of the ocean or close to the bottom. These are called ROVs, and we'll talk more about that. So the combination of knowing where we are, knowing what the seafloor looks like, and being able to go down there and see what's going on from the surface is what's opened the door for modern marine field geology. So before about 1990, it was not easy to locate one's position in the oceans. So because of that, seafloor bathymetry was not very precise. Now here's an example. This is some work I did, published this paper in 1984. This is a submarine volcano. This depth is in fathoms. Now we report everything in meters, but back then we were still doing that. So 700, 600, 500, 400, 300, 200. Some it's about 100 fathoms, right? That's about 600 feet below sea level. And then in the center, you can see there's a little caldera. That's 2 nautical miles. So that caldera is like, mile and a half this way and mile this way. And the dashed lines are showing you the ship track. So this is basically the ship was basically doing echo sounding and generating something like this. This is the record we would get, right? There's a little caldera. This area is called Esmeralda Bay, okay? So, you could do okay, but that was a lot of ship time to do that much back and forth. That would take you a day. So now we have new types of ways of getting seafloor. One of them is at the very large scale. With seafloor satellite altimetry basically maps Earth's gravitational field, and that's a reflection of the depth to the seafloor in the oceans. So you can see things here, the entire ocean. You can see big transform faults in here. You can see how shallow the spreading ridge is up by Iceland and how it gets deeper as you go farther south, but it's still present. Very hard to see the East Pacific Rise in here. Can't. That's the hotspot chain of Hawaii. This is the trench, right? Where the plates go down. So this is amazing. 1997, be able to map at some, gross scale the entire seafloor. But now we've got a new technology, and we're going to watch a video.
I'm Bill Hamblett, the Editor-in-Chief of Proceedings at the U.S. Naval Institute. Today I'm reading from the Oceans column, Mapping the World Ocean Seafloor by Don Walsh from March 2020. According to the National Oceanic and Atmospheric Administration, only 10% of the 140 million square miles of the planet's seafloor has been adequately mapped. Other online sites mention a range of between 5 and 20%. Some of the measurement differences relate to the dates of the estimates and how they were calculated. Adequately is an important word. It refers to the ability to resolve sea bottom features. For example, if resolution is 3 miles, it means that any features smaller than that will not be seen. Since the beginning of the 20th century, maps of the seafloor have been made by interpolating between sparse soundings, either from lead lines or single-beam echo sounders, with very limited resolution and spatial coverage. Toward the end of the 20th century, techniques were developed to estimate seafloor depth from satellite-based measurements, producing the first seafloor maps with global coverage, but with resolution of only 12.4 miles. By 2016, this resolution had increased to 3.1 miles, but this is hardly a detailed map. By comparison, NASA has been able to map the surface of Venus to 328 feet resolution and Mars to 66 feet. And closer to home, the best moon map resolution is 7 feet. The overused saying, "We know more about the moon's behind than the ocean's bottom," has a ring of truth. Highest resolution knowledge of seafloor topography is vital to support commercial, scientific, and military use of the oceans. So how can this vast, somewhat unknown area be mapped with sufficient detail? The classical and prevailing means is with oceanographic research vessels and specialized hydrographic survey ships. It is estimated that one ship would need 350 years to accomplish 93% coverage with current state-of-the-art mapping systems. The cost of such an effort is large, somewhere between $3 and $5 billion, but this is not much different than the cost of 1 or 2 Mars missions, and perhaps a small price to pay to have detailed maps of our own planet. New technology, however, may significantly reduce the cost. An attractive partial solution is to use fleets of long-duration underwater drones programmed to do multi-beam acoustic mapping. They would be large, autonomous, untethered vehicles, AUVs, essentially unmanned submersibles. Large numbers of them, or swarms, could be controlled and coordinated by ships. Some AUV users claim they could do surveys with the required precision 60% faster than shipboard systems. Some experimental AUVs already have made test voyages across the Atlantic and Pacific Oceans. But the idea of autonomy is not exactly correct. All survey AUVs will require motherships for voyage monitoring, control of navigation, recharging onboard power, and downloading survey data. A properly configured mothership could control and service several AUV hydrographic survey submersibles. This would multiply the amount of seafloor mapping per unit of time compared with what can be done by a single hydrographic survey ship. At some future time, the mothership might even be another type of drone designed to control its own fleet of AUVs. In 2019, a prototype unmanned surface vessel was tested as a mothership for a single AUV, and the results were promising. Developing new data collection platforms such as spacecraft and AUVs and USVs is but one path to greater productivity. Another is more aggressive global collection and management of existing data through international cooperation. Such data harvesting can be anecdotal from private and commercial sources or professional from hydrographic survey ship operators. Today, there is a major international effort to produce a publicly available global seafloor topographic map by 2030. It represents continuation of the historic work of the General Bathymetric Chart of the Oceans, or GEBCO, activity that began at the start of the 20th century. In 2016, it was accelerated by Japan's Nippon Foundation, which joined and provided startup funding to organize the effort. The new project is called the Nippon Foundation GEBCO Seabed 2030 Project. Management is provided by the International Hydrographic Office in Monaco and the UN's International Oceanographic Commission in Paris. For more information, see www.gebco.net/about-us/overview.
So this is that, obviously for this big seafloor mapping project, there's going to have to be a remarkable GIS to go along. All right, so you can see the improvement, the level of detail that we can get with swath mapping here on the right compared to what we used to do, with just single channel echo sounding. Now, here we're looking at some bathymetric images of a fast spreading ridge and a slow spreading ridge. So we're going to talk about fast and slow spreading ridges quite a bit. And so a fast spreading ridge here, we got one that's spreading at 91 millimeters per year. This one is slow, or we might call it intermediate spreading. It's 57 millimeters per year. And the bathymetry that you see changes with spreading rate. And in fact, this is a very powerful clue for spreading rate, is the bathymetry. These slower spreading ridges have this axial rift that Marie Tharp noticed in the Mid-Atlantic Ridge. The Mid-Atlantic Ridge is a slow spreading ridge. This is a profile, topographic profile along this line, right? So these lighter areas are shallower, these darker areas are deeper. So you've got the rift, and it's separated by two highs like this. Whereas in the East Pacific rise, it's not anything like that. You've got this axial ridge, right? So it's a completely different physiography or bathymetry. And that's one of the key things that will probably show up in the midterm, When I say probably, I mean it will. All right. So seafloor spreading, Hess and Dietz, this got, people like that, but it's like, okay, well, what else does it explain? A real advance in our understanding of any field is going to explain some things that it wasn't intended to explain. And that brings us to Vine-Matthews-Morley. This is the seafloor magnetic fabric understanding that happened in 1963. And this couldn't be really resolved until they'd worked out the magnetic reversals on land. All right, now remember the Earth's magnetic field periodically reverses or flips. Some of you might be thinking, okay, didn't he just go over that? And the answer is yes, I did. But this is different, right? The kind of paleomagnetics we were talking about last class happens on land. And it's geologists go out with drills and they core, and this is quite different. But what happens on the seafloor is caused by the same sorts of things. It's basalts capturing Earth's magnetic field at the time that these basalts formed. So reversals were discovered by two Frenchmen, Bernard Brunis and Émile Cartignet, in 1906. And it was Elsasser in 1946 who argued that convection in the liquid iron core was responsible for Earth's magnetic field. And you can see here we've got a normal polarity, and here's a reversed polarity, right? The magnetic field lines are the same, except the magnetic north is in a different direction, right? Here. Now, seafloor magnetic anomalies are collected by towing an instrument behind a ship over the seafloor. There's no actual collecting of samples. Now you can see why the military would be interested in this technology, because this thing is actually designed to capture metal submarines, right? The metal submarine should really have a strong magnetic signal. But in order to do that, you need to know what the ambient magnetic field is. Okay, so we need to remind you, the total magnetic field values can be measured to plus or minus 1 nanotesla, which is 1/50,000th of Earth's magnetic field. Okay. Now, continental magnetization tells you nothing about the age of the rocks, but it's still useful. This is a magnetic map of the United States. It's a really remarkable fabric that is of geologic interest, but it's quite different than seafloor magnetic fabric. And I'll show you this, how strikingly different the magnetic fabric of the continents and the oceans is. Look at this. There, the white line is the Mid-Atlantic Ridge, and the magnetic fabric in reds and blues is basically mirroring it. So in contrast to the magnetic signature of the continents, which bears no relationship to any simple geologic process, seafloor magnetics are symmetric around the spreading axis where they formed. These seafloor magnetic anomalies reflect the polarity of the Earth's magnetic field, north or south, at the time the seafloor formed, right? And basically when the erupted basalts cooled below the Curie temperature and locked in their thermoremnant magnetization. Now, this is what got Mason and Raff going. So they were out mapping the seafloor, magnetically mapping the seafloor for the military, for the Navy, and they discovered this kind of a pattern. Now, it looks kind of like the skin of a zebra, doesn't it? And basically, the blacks are the zones where the magnetic anomalies are positive, and the white areas are where the magnetic anomalies are negative. And they noticed that these anomaly patterns were disrupted by these major fracture zones, which they didn't understand at the time. There's the Mendocino fracture zone, which we now know links up with the San Andreas fault that comes through here. This is the Pioneer fracture zone, the Murray fracture zone. And the typical anomaly was on the order of 10 to 20 kilometers wide, with amplitudes of 500 to 1,000 nanoteslas. Something along that line might be in the midterm too. And it became quickly understood that the magnetization is mostly in the basaltic lavas and dikes, which we call layer 2 in a couple of lectures ago. Okay, those are things where the basaltic rocks cool very quickly, and so they lock in the magnetic field. Now, they also noted that the magnetic anomaly stripes were symmetric around the Mid-Atlantic Ridge. This was very interesting. So this is the Mid-Atlantic Ridge, the red thing coming down, and then this patch was mapped. This is an area was a lot of interest, still has a lot of interest to the Navy, because that's where the Russian Soviet submarines come through. We now understand these magnetic stripes to be caused by episodic reversals of Earth's magnetic field, which were captured by lavas when they were erupting from the spreading ridge. Like this. Here's that pattern. Here's the way it's interpreted. This is in the past. This is today. So in the past, you had spreading there. Each half went one way or the other by seafloor spreading, a new zone in here, new zone in here. So these are the normal magnetic polarities, sort of separated by colors. This is in it, the same thing we're seeing in a very simplified way, right? This is geologically more complex. This is sort of schematized. So this would be the way you would show it on a profile, positive and negative anomalies. And the ridge is there. So if seafloor spreading happened, you would expect this to be symmetric around it, right? This anomaly happened at the same time as this anomaly. And it's older. These two anomalies are older than these anomalies in the middle. So this basically lays out how the oceanic crust formed at a mid-ocean ridge.
I have a question.
Yes, go for it.
As far as being able to detect positive, negative anomaly on these pole reversals, what is it a pretty abrupt thing, or does it take, a couple hundred years for it to completely flip, or is it? Do we?
That's an area of active study. It seems to happen very quickly, but I can't tell you the units. We'd have to get at the paleomagnetic expert, but it's not very slow. All right. So the rates of magnetic reversals have changed with time in a way we don't understand. So this is looking at the last 160 million years of Earth's history. The age of the oceanic crust, as you know, is much younger than that of the continents. And the oldest oceanic crust that we have is on the order of 180 million years old. And so we now name these anomalies, right? Each of these spreading anomalies that we see here, or here, or here, they're assigned a number, and that number is a little complicated. So the most recent anomalies are anomaly 1. The oldest ones in the Cenozoic and late Cretaceous are anomaly 34. Then we have a time when there was no reversals, about 40 million years. It's called the Cretaceous superchron. And then before that, there's another set of anomalies, and those anomalies are numbered M0 to M27 to distinguish them from the younger anomalies, right? And they're numbered. This is M0, and then this would be M27 back here. So the other thing you can see here is that the rates of reversal has been changing. Back here, this is in late Jurassic and early Cretaceous time. The reversals became slower and slower and then stopped. And then this is about the beginning of the late Cretaceous. When the reversals started again, they were quite slow. The reversal rate was on the order of 1. And then, up until recently, it was just increasing until it reached a maximum of 5. And that's where we are today. Now, this is an observation. The Cretaceous superchron is a thing. Nobody's really explained this yet. All right. So seafloor spreading and magnetic reversals led to the Vine-Matthews hypothesis of 1963. Now, you remember I called it the Vine-Matthews-Morley hypothesis. So the reason I've added Morley on is because he should also get credit because he articulated the idea about the same time, but his manuscript was rejected by both Nature and the Journal of Geophysical Research, as the reviewers just thought it was too crazy. So he gave up. He should have kept trying to get it published, but it's basically the Vine-Matthews hypothesis. So The Vine-Matthews-Morley hypothesis: seafloor magnetic lineations form when basalt erupts from the mid-ocean ridge, produce new oceanic crust. The cooling magma, as it's erupted, passes through the Curie temperature, acquiring the magnetization with the same orientation as the ambient geomagnetic field. Seafloor spreading is continuous, producing new oceanic crust symmetric around the ridge axis. But geomagnetic reversals are episodic, and they are preserved as thermoremnant magnetization, producing the parallel regions of normal and reverse polarization. Positive magnetic anomaly is over seafloor with a normal magnetization like that of today, negative over those with the reversed magnetization. Easier, and this is going to also be on the midterm. It's easier to detect anomalies at high latitudes because the TRM magnetic vectors dip steeply, harder to detect at low latitudes where the magnetization is horizontal. And also in general, the geomagnetic field is weaker at low latitudes. So here is an anomaly at different latitudes. This is kind of a profile, right? This would be the axis of symmetry here. And this is at the equator, and this is at 90 degrees. So you get the same reversal sequence will give you stronger anomalies at high latitudes than at low latitudes. In addition, north-south profiles give the strongest anomalies, and east-west profiles give weaker anomalies. So here's the same reversal sequence for a north-south profile across it versus an east-west one. That's 500 nanoteslas. Now, before we could really use magnetic anomalies to infer the seafloor ages, we had to come up with a geomagnetic timescale, that is magnetostratigraphy. At first, the timescale was only good back to about 5 million years. This is it going back to about 5 million years here. 1, 2, 3, 4, 5. So geologic time, Pleistocene here, Pliocene here. So this was worked out from studying sequences on land. So black is normal polarity, like we have today. White is reverse polarity. This is worked out from lava flows on land. So these are numerical crons, right? You don't have to memorize these, but there's 1N, 1R. Within, say, 1R, there's a short normal period. So it's got a little bit more subtlety. You don't have to remember this. This is just for the experts. And then these numerical crons are given names: Brunis, Maruyama, Gauss, Gilbert. Those are just the last ones. So this is an interesting book that some of you might be interested in. This is The Road to Jaramillo, Critical Years of the Revolution in Earth Sciences. So Jaramillo Creek is in the Valles volcano of northern New Mexico. The Jaramillo normal epoch, which is right here, was a short excursion in the Maruyama reversed epoch, and it was named for rocks at the type locality. So this book is the story of how scientists produced the discoveries that brought around the plate tectonics revolution. Anyway, some of you might enjoy it. All right. So here we've got our magnetic sequence for the last 5 million years, right? And here we've got a magnetic profile across, the Juan de Fuca Ridge off the coast of Oregon and Washington. There's the spreading axis. So if we want to explain this, we have to come up with a computer model which incorporates this reversal sequence and solves for a spreading rate, right? This is going to be expanded or contracted depending on the spreading rate. So here we're using that magnetic time scale with the magnetic anomalies. So here are the magnetic profiles. Here are models with inferred spreading rates. So here's the Reykjanes Ridge up in the North Atlantic, the South Atlantic, Northwest Indian Ridge. This is the East Pacific Rise and the Juan de Fuca. And what you'll see here is the spreading rate, basically using this kind of a procedure that we just talked about, right? This time scale, this observed profile, and coming up with the best fit model in terms of spreading rate to make it. So here you can see the spreading rates, 10 millimeters per year, 15 millimeters per year, 15 millimeters per year, 29 millimeters per year, 44 millimeters per year, right? It's the exact same magnetic sequence, and whether it's compressed or expanded is simply how fast that spreading is occurring. So you get a lot of interesting information from these kinds of studies. Right? We use magnetostratigraphy to calculate the age and spreading rates for the seafloor. Now we've got this entire reversal sequence, and it goes back even farther than that, right? And do pay attention to the fact that the magnetic anomaly numbers, right, here we're going from 1 to 24, are not the same as the time scale. The time here is going from 0 back to 55 million years ago. I mean, they are linked, but they're not identical. So now we can come up with a list of ridge spreading half rates and full rates. So here we've got a list of these different ridges and their observed spreading rates. They vary a lot. Pacific, we'll see over and over again, is the fastest spreading. Oh, wait a minute. There we go. Oh, that's Pacific too. That's East Pacific Rise. And very slower spreading in the Atlantic and in the Indian. Now, we could report these in millimeters per year or centimeters per year. And millimeters per year is preferred. And the reason for that is because millimeters per year equals kilometers in million years. And it's just easier to calculate how far something has moved in geologic time with kilometers per million years than millimeters per year. So that's why we prefer that rather than centimeters per year. And so we can generate this kind of a map. This is basically dividing ridges into slow, intermediate, and fast. This is the fast spreading ridge, which then turns into an intermediate spreading ridge, which then turns into a slow spreading ridge. So in general, fast is 90 to 180 millimeters per year. That's the full rate. Slow is 10 to 50 millimeters per year, and intermediate in between, 50 to 90. And we can see the effects of those spreading rates in how much crust is produced on the seafloor per unit of time. Look at this red zone. We've seen this map before, but this is going back 10 million years. And look how broad of a region has been created in 10 million years in the Eastern Pacific compared to the Atlantic, where spreading rates are much lower. So just the width of this red area, gives you something information about the spreading rate. So basically, since the 1960s, geoscientists have been working out the magnetostratigraphy back to the mid-Jurassic, about 160 million years ago. And basically, that's the age of the seafloor. We can't go any farther back than that for the seafloor, based on the seafloor, because the oceanic crust isn't older than that anywhere. We can reconstruct the reversal rate perhaps from working on continental rocks, but that's much less continuous than we get from the seafloor record. Okay, we've already said this. So when you start doing these kinds of reconstructions, you focus in on one anomaly rather than another, right? Some of the ones that are more obvious to the people that do this work are anomalies 5, 12, and 13 because of this intermediate 21 to 26. So there's some evidence that seafloor spreading rates are changing with time. Now, one of the key things that led to sort of not proving the idea, nothing is ever proved in science, but basically settling the controversy was oceanic drilling around the southern Atlantic spreading ridge, where they had identified magnetic anomalies, and from that inferred the age of the oceanic crust. And then they drilled it, right? These are all drill holes, 14, 15, 16, 17, 18, 22. And you can see the ones that are closest to the ridge, like 16, they're youngest, and older ones farther away, they're much older with distance. And if you simply, you couldn't really get a good age on the basalts, but you could get a good age from the age of the sediments immediately lying on top of them. And if you did that, the age of the oldest sediment on top of the oceanic crust in the drill hole looks like that as a function of the distance from the ridge. It's exactly what you would expect, you'd predict from seafloor spreading. So this was basically a test, and the hypothesis was supported by that test. Now, this is our present understanding of the Earth's magnetic reversal record, right? We talked about how there's been lots of reversals in the Cenozoic, and then here's the magnetic quiet period and the Cretaceous, and then these are the M series reversals from before the Cretaceous quiet zone, quiet period, or superchron, whatever you want to call it. You don't have to memorize this, but it is useful to know that going from 1 to 34, you're basically going back to the magnetic quiet period, and then the M series date from before that. And this map of seafloor age that you will see in many places is based on interpretation of seafloor magnetic anomalies. So we can use these magnetic anomalies to define isochrons or regions of the same area. And then you can fit together isochrons on either side of a ridge to reconstruct the evolution of an ocean basin and the motions of the attached continents. So that's what we're doing here. So that's at 81 million years ago, 63, 53, 38. And then finally, Wilson came up with transform faults, the idea of 1965. So transform faults are required because spreading ridges are constructive or divergent plate boundaries require complementary subduction zones, destructive or convergent plate boundaries. And the third dimension requires a plate boundary that's neither constructive nor destructive. And Wilson, 1965, identified a new class of faults, which are transform faults, which is where two lithospheric plates move past each other. So we can talk about transform versus transcurrent faults. So this is a transform fault. This is a transcurrent fault. The transcurrent fault, this fault is separating these two geological items, could be a bed or a pluton or something, and they're continuous all the way through. So if you see this kind of an offset, you'd go, that's a left lateral strike slip fault. You could call that a strike slip fault. But what Wilson saw was something different. He said, look, these features here of zones of seafloor spreading from Dietz and Hess are connected by a fault that's not a seafloor spreading zone. And this is the only active part of the fault. These parts off to the sides are not active. This plate is together. This plate is together. This is a plate boundary. He says this is a transform fault as opposed to a transcurrent fault. The offsets are different. This one is right lateral. This one is left lateral. Okay. This was like, what? That can't be. So it's like somebody needs to bring in some information to prove that it's wrong or not. And so there's many kinds of transform faults. We'll talk more about these. We'll have a whole lecture on them. Here's one that's combining, looks like the one we just saw with two spreading segments, and they're, the transform there is letting these two plates move past each other. This is another one that's bounding between a ridge and a subduction zone, convergent plate boundary, another one. Lots of different ones. Now, what convinced people that Wilson was right was earthquake studies in the Mid-Atlantic Ridge. Here's Africa, here's South America, this is the Mid-Atlantic Ridge. There's a lot of transforms in here. And what Sykes in 1967 showed was that the focal mechanisms, which, as we'll learn, are related to the displacements on the faults, were consistent with what Wilson predicted. And it was that confirmation from independently from the geophysical community that convinced people that Wilson was right. So here we've got an example of, two spreading ridges connected by a transform. This side of the ridges is moving as a single plate, although there's a morphological feature on the seafloor called a fracture zone on both sides. But the only part of the fault that's active is this part in here, the transform fault. So transform faults and fracture zones are related. And a good example of a continental transform fault is the San Andreas fault, which allows this side of the bound plate to move independently of this side. And we see that in big earthquakes that have happened along the fault, 1906, 1857, 1680.